electron. A smartphone screen flickers to life. A thumb swipes across the glass, triggering a cascade of electrical signals. Deep within a human brain, a neuron fires, sending a microscopic pulse of electricity across a synaptic gap. Across a vast landscape, the steady hum of a power grid maintains the rhythm of a city. These are seemingly unrelated events. They are different scales, different speeds, and different worlds. Yet, they share a single, invisible driver. Everything we touch, every thought we process, and every machine we build relies on a single, tiny particle. We call it the electron. It is the architect of modern life, the silent engine of the universe. It is small beyond comprehension. The mass of a single electron is roughly 2,000 times smaller than that of a hydrogen atom. We have searched for its edges, but it remains elusive. Experimental measurements suggest its size is smaller than 10 to the power of -18 meters. In the textbooks, we often picture it as a little billiard ball, a solid point of matter moving through space. This view is a useful lie. It simplifies a reality that is far more strange and far more beautiful. Physics tells us the electron is not merely a particle, but a disturbance in a vast, invisible field. It is a ripple in a cosmic ocean, a point of tension in a fabric that permeates everything. This is the great tension at the heart of modern physics. On one hand, we have the point-like particle, a simple dot with no internal structure. On the other, we have the complex reality of quantum field theory, where the electron is inseparable from the vacuum itself. To understand the electron is to understand the very rules by which the universe operates. We must look back to the moment the atom was first broken open to find it. The pudding and the bullet. By the late 1800s, the atom was considered an indivisible, solid sphere. It was the final, unchangeable building block of matter. But in a laboratory in Cambridge, J. Thomson began to look more closely at the vacuum tubes used in cathode experiments. He noticed something strange. A beam of particles was being deflected by magnetic and electric fields. These were not waves of light. They were something much smaller. In 1897, Thomson made his breakthrough, proving that the atom was not a solid, unbreakable unit.
I believe these are the constituents of atoms.
Thomson needed a way to visualize this new reality. He proposed a model that became famous for its culinary metaphor. He imagined the atom as a sphere of positive charge, with tiny, negatively charged particles scattered throughout it, much like sultanas in a Christmas pudding. This was the plum pudding model. It was a way to explain how an atom could be electrically neutral while still containing these small, mobile components. At the time, it was a revolutionary way to see the invisible architecture of the universe. Science was not a consensus, however. A fierce debate raged across the English Channel. On the continent, many scientists looked at the green glow emanating from vacuum tubes and saw only electromagnetic radiation, like light or radio waves. They believed the glow was a wave phenomenon. Thomson disagreed. He insisted it was caused by the movement of actual, physical particles. The truth lay in the particles. The pudding model would not last. A student of Thomson, Ernest Rutherford, set out to test the internal structure of the atom using alpha particles, which are heavy, positively charged particles. He fired these particles at a very thin sheet of gold foil. If the atom was a soft pudding, the particles should have passed through with almost no deflection. Instead, the results were chaotic. Most passed through, but some were deflected at massive angles. A few even bounced straight back toward the source.
It's like you fired a 15-inch shell and a piece of tissue paper and it came right back at you.
The atom was not a soft pudding. It was mostly empty space, with a tiny, incredibly dense, positive core at its center. The solid billiard ball had been dismantled. In its place stood a complex system of subatomic parts, a structure that would eventually lead us to the modern understanding of the electron as a particle with a mass 2,000 times smaller than hydrogen. By the 1920s, the atom had become a battlefield of conflicting ideas. The old rules of physics, the laws of Newton and Maxwell, worked perfectly for planets and magnets. But they failed when applied to the subatomic scale. The electron refused to behave like a tiny billiard ball. It acted like a wave, then a particle, then a cloud. To describe this chaos, scientists needed more than just observation. They needed a new language entirely. Enter Paul Dirac. He was a man of profound mathematical clarity. While others struggled to reconcile the strange behavior of quantum mechanics with the speed of light, Dirac turned to pure abstraction. He did not start with an experiment. He started with a problem of symmetry. He sought a way to marry Einstein's special relativity with the quantum world.
The mathematics seemed to require this single equation to end up as four very intimately linked equations.
The result was the Dirac equation. It was a masterpiece of mathematical elegance. But it did something unexpected. When Dirac wrote down the maths, the equation did not yield a single solution. Instead, it split. It required for distinct components to remain consistent. These components described the electron spin and its energy, but they also revealed a terrifying, beautiful possibility. The maths was telling him that for every particle, there must be a twin. Dirac had conjured a ghost. The mathematics predicted a particle that looked exactly like the electron, but with a positive charge. It was a mirror image. At the time, no such particle had ever been seen in any laboratory. It was a theoretical phantom, a mathematical necessity that seemed to defy the known reality of the universe. For a few years, it remained a haunting suggestion of a hidden world. This was the moment physics shifted. The electron was no longer just a component of matter. It was part of a much larger, more symmetrical cosmic dance. The ghost was about to become flesh. The mirror world. By the late 1920s, the electron was no longer just a tiny speck of matter. It was a mathematical problem. Paul Dirac sat with a single equation, attempting to reconcile the strange rules of quantum mechanics with the laws of special relativity. The maths was stubborn. It refused to behave. To make the equation work, Dirac had to accept a startling consequence. His mathematics suggested that for every particle, there must exist a twin. This twin would possess the exact same mass, but its electric charge would be reversed. It was a mathematical necessity that defied common sense. It suggested a mirror world, a shadow reality where everything was inverted. The theory was elegant, but it was purely abstract. It was a ghost in the machine of physics. Then, in 1932, Carl Anderson looked through a cloud chamber. These devices use supercooled vapor to make the paths of subatomic particles visible as streaks of mist. Anderson was studying cosmic rays. He saw something impossible. A particle was moving through the chamber, but its path curved in the wrong direction. It had the mass of an electron, but its charge was positive. This was no mathematical error. It was the positron. The mirror twin had finally been seen. The discovery of the positron changed everything. It was the first time humanity had encountered antimatter. An antiparticle is not just a different kind of thing, it is a structural reflection. If an electron meets a positron, they annihilate. They vanish in a flash of pure energy. This is not just a curiosity for the laboratory. The existence of antimatter changed our fundamental understanding of the cosmos. It suggested that the vacuum of space is not empty. Instead, it is a boiling sea of potential, where particles and antiparticles are constantly flickering into existence and then disappearing. The electron had become a gateway. By understanding this single, tiny particle, we unlocked the door to the very fabric of the universe. It showed us that the laws of nature are built on a profound sense of balance. For every action, there is a reaction. For every particle, there is a shadow. This search for symmetry would drive the next century of physics, pushing us toward the most extreme environments in the known cosmos. For decades, we pictured the electron as a tiny hard marble. A discrete object, like a billiard ball, bouncing through space. This was a comforting image. It made sense to the human mind. But as we looked closer, the marble began to dissolve. The particle refused to stay in one place. It behaved more like a vibration, a disturbance that could be in many places at once. We had to abandon the idea of the electron as a lonely wanderer. Instead, we must see it as a ripple in a vast, invisible ocean. This ocean is the quantum field. The electron is not an object moving through space. It is a local excitation of the field itself. When you pluck a guitar string, you create a note. When you pluck the electron field, you create an electron. This shift in perspective changed everything. It led to the development of quantum electrodynamics, or QED. This theory describes how light and matter interact with profound precision. It is arguably the most successful theory in the history of science. When physicists calculate the properties of an electron, the maths matches reality to 12 decimal places. It is a level of accuracy that borders on the miraculous. But even with this precision, the electron remains a strange, crowded thing. It is never truly alone. It is constantly surrounded by a frantic swarm of virtual particles. These are particles that blink in and out of existence, appearing and disappearing so quickly they cannot be directly seen. They form a chaotic cloud around the electron's core. This cloud actually changes how the electron behaves and how it interacts with the world. Such clouds are part of the fabric of reality. We cannot strip the electron away to find a simple, naked point. What we observe is a complex, dynamic system. The electron is not just a piece of matter. It is a continuous, shimmering event within the field. The electron is not alone. It belongs to a family of particles that share its charge, its spin, and its fundamental identity. These are the leptons. Among them, the muon and the tau are the electron's heavy, unstable cousins. They are identical in every way that matters to the electromagnetic force, yet they possess a strange, varying weight. They appear in our detectors as fleeting ghosts, decaying in a fraction of a second into lighter particles. The differences between them are stark. While the electron is light enough to orbit an atom, its relatives are far more massive. The muon is roughly 200 times heavier than the electron. The tau is even more substantial, weighing in at 3,500 times the mass of its lighter sibling. This mass hierarchy is a profound puzzle. In the equations of the Standard Model, these masses appear as arbitrary numbers, values that must be measured rather than predicted. Physicists look for a pattern in this triplet. We seek a hidden logic that dictates why nature chose these specific, wildly different scales. There is no obvious reason why the tau should be so much heavier than the electron. This lack of a predictable pattern suggests that our current understanding is incomplete. We are looking at a fragment of a larger, more elegant structure, a symmetry that has been broken by the universe as it cooled after the Big Bang. To find this order, we build machines of immense scale. Deep beneath the Earth, in massive circular tunnels, particle colliders smash matter together at near-light speeds. We are searching for grand unification. This is the dream of a single, perfect theory that merges the forces of nature into one. In these high-energy collisions, we hope to find the symmetry that existed at the beginning of time, a state where the electron and its heavy cousins were indistinguishable. The search continues. Every new measurement of the muon's properties or the tau's decay provides a clue. We are hunting for a signal that the chaos of the subatomic world is actually a mask for a deeper, more beautiful mathematical harmony. The final frontier, point or string. We have spent a century probing the limits of the very small. Using massive particle accelerators, we smash matter together to see what lies within. The data is startling. We have found that the electron has no measurable size in our current experiments. We know it is smaller than 10 to the power minus 18 meters. To put that in perspective, an atom is a vast, empty solar system compared to the scale we are discussing. We are approaching a wall. A limit where our tools can no longer see the shape of things. This leads to a profound paradox. In our standard models, we treat the electron as a point-like particle. It is a mathematical dot. It has mass and charge, but it takes up no space. It has no internal structure. If it is truly a point, it is a zero-dimensional object. This is a difficult concept for the human mind to grasp. How can something exist, move, and carry force, yet occupy no volume? It is a mathematical convenience that works perfectly in our equations, yet it feels physically incomplete. Perhaps the electron is not a point at all. There is another possibility. Some theorists suggest that the electron is actually a tiny vibrating string. In this view, the particle is not a dot, but a fundamental filament of energy. The different properties we observe, like mass and spin, would simply be different notes played on that string. This is the core idea of string theory. It promises to unify gravity with the quantum world, but it requires us to accept that the fundamental building blocks of reality are much more complex than simple points. The debate remains unresolved. We are caught between the precision of our measurements and the elegance of our theories. The electron remains a gateway. It is the smallest thing we can truly grasp, yet it hints at a deeper, more complex architecture of the universe. We continue to look for the truth hidden within the void. The mystery of the electron is, in many ways, the mystery of everything.